Is it 10? No, it's 2:09. We'll get started in a minute here. So we're going to go over some web work problems from various instructors just because people ask, and also just to make sure you're all feeling all right about how to enter things in web work because it can be kind of a pain. I think at least Varn did. Maybe I don't know about the other professors. I know Varn had like kind of a first assignment that had like some practicey kind of questions to help you get used to entering things in web work. I'll say from experience, if you're pretty confident your answer is right and it's not coming out right, read the question really carefully. Because I've certainly, for example, there was a problem where we were asked to find some point, the maximum or minimum, and we were sure we had it right. We kept entering the first two coordinates of the point, but there was actually a point in three-dimensional space. We had to enter X, Y, and Z coordinates, and all of us missed it because we just didn't read the question very carefully. So if you feel like you've got the answers right, but it's not coming out right, it's a good indication that you might want to go back and just read the question more carefully. Let me pin my video. Let me do that. Let me, for those of you who are not in person, which is totally fine, let me give you the attendance link so you can fill that out, please. Oh my, why is this gigantic? Okay, there, it's not gigantic. Okay. Terrible. Here's the link to the attendance form. Please fill that out when you have a second. Cool. All right, so let's look at these questions that have to do with composition of functions. So I'm going to write some stuff down and then we'll look at it. So our functions are f of x equal to the square root of x plus 3 and g of x equal to the cube root of 6 minus x. Those are mine. Yours are probably slightly different or not. And then they're asking us, so I'm just going to read all four of these and then we're going to do them. So they're asking us for the domain of f circle, or so two things. They're asking us to find all these compositions, f circle g, g circle f circle f, g circle g. I would encourage you to read that as f of g of x and g of f of x and f of x and g of x. And then they're asking us to find the domain of all of this as well. Cool. We'll come back. Why you should not be over here. You should be over here. Better. Maybe. I don't know. I hate this thing. I wish it would just disappear. And it does sometimes. I need the other thing. There you are. Cool. So let's go ahead and look at. Actually, let's not look at any of that just yet. Let's do something else first. Sorry, it's never in the right place. It's just never going to be in the right place. Let's find the domain of each of these functions on their own first. So for this function, f of x equal to the square root of x, an even root, so the insides have to be non-negative. So we're going to start by setting x plus 3 to be greater than or equal to 0. And then we get x bigger than or equal to negative 3. So if you want to write the domain using interval notation, it would be everything from negative 3 inclusive to infinity and beyond. Lighten that up a little bit. If you ever have trouble seeing something, let me know. I feel like you all see this okay? All right. And then for g of x, domain's everything. There's no domain issues here because that's a cube root, and odd roots, you can take the odd roots of positive and negative numbers without issue. So any real number is a valid choice for the domain of g of x here. All right, let's start with f of g of x. So I personally like to work from the inside out. That's usually the best way for the composition of functions, but really either way is fine. So and I'll do the second one from the outside in. No, I'll do this one both ways. So this one I would first write as f of the cube root of 6 minus x. The inside out, working from the inside out actually is best, especially if you're talking about a domain. So I'm going to say something now, even though it's not super applicable here. Whenever you're doing a composition of functions and you're asking about the domain, we always have to obey the domain of the inner function. And then additionally, there might be something that the composition also makes us obey. But first and foremost, the inside function, for sure, domain has to be obeyed, even if it looks like it's not there if you simplify later on. So here, no restrictions, right? This function here, my pen, right here, right in front of your face. This function, we know the domain is all reals. So we're not going to worry about it. We're going to move on. We're going to plug that function into the function f. So f of x is the square root of x plus 3. F of some new stuff is the square root of that stuff plus 3. And I really, really, really can't recommend enough if you're doing a composition of functions, wherever you would have written an x, write a parentheses. And then go and fill in the parentheses with whatever your inner function is here. In this case, the cube root of 6 minus x. You probably don't actually need the parentheses, but I like to write them. Okay, so I'll point out that this is how we would, well, this is how I would write using like my pen, how I write the function. But if I'm going to type it into WebWork, it's almost always easier to write radicals as rational powers. So instead of writing the cube root, I'm going to write that stuff to the 1/3 power. Instead of writing the square root, I'm going to write that all as raised to the 1/2 power. So when I do this in WebWork, I'm going to write this as the insides first. I'm going to have 6 minus x to the 1/3 power plus 3, and then all of that raised to the 1/2 power. That's going to be the easier way to input it into WebWork. Okay. Well, and let's do that right now. It doesn't matter how many chances I have, right? But come on in. Where'd you go? WebWork right there. How many? I have 6 attempts. Okay, that'll be enough. So you can use parentheses or brackets. I'm just use parentheses and say left, left. I have a 6 minus x to the 1/3. So to do the exponent, it's that little caret symbol that's above the 6, right? Oh, question. Can I zoom in? Can I zoom in? Can I zoom in? Good. Oh, yeah. No, I can do that. Yes. Cool. So I have 6 minus x raised to the 1/3 power. I can't just write 1/3 like that. I'll show you why. And then I have plus 3, and then close the parentheses, raised to the 1/2 power. If you're not sure about your answer being typed correctly, don't hit submit, hit preview. And that does not look so hot, right? I accidentally did 6 minus x to the 1 and then all divided by 3. So if your exponent is more than 1 character, you have to put it in parentheses. So I'm going to write this as 6 minus x to the parentheses 1/3, close the parentheses, plus 3 to the power of parentheses 1/2. And now it should look good. Looks good. Okay, let's, instead of, okay, we can submit it, fine. Let's submit it and see what happens. Right on, we got it right. But we got all the other ones wrong, and I think we used up one of our chances, so I wouldn't submit until I'd answered all the things, unless, I don't know. You can do whatever you want, but that's what I would do. So let's go ahead and now find the domain for this function. So we already said the inner function here isn't going to matter. So let's deal with the outer composition. So I do have a square root of some stuff. So I need to set that stuff to be greater than or equal to 0. As you probably have noticed, most of the time I would approach something like this by factoring, but factoring is not really an option here. So I'm really going to have to just try to isolate x. So I would bring everything. No, I would not bring everything. I would kind of separate the 6 minus x to the 1/3 from the positive 3. So either way you like. I'm going to bring the negative 3 to the other side. So I have 6 minus x to the 1/3 needs to be bigger than or equal to negative 3. The nice thing about odd roots is that you can undo them with odd powers, and there isn't any of that plus or minus stuff. It's safe to do it, and it's also not gonna destroy your inequality. Is it not gonna? Yeah, you should be fine. Yeah. You know what? Let's do it and find out. So I'm gonna raise both sides to the 3rd power to undo that 1/3 root. So then I'm gonna have 6 minus x bigger than or equal to negative 3 to the 3rd is negative 27. I would probably choose to add x to both sides and to add 27 to both sides. 6 plus 27 is 33. And if I'm adding x to the right, it's just x. So it looks like my domain should be x is less than or equal to 33, which would be everything from negative infinity up to 33. But before we just answer it that way, let's pick a number and plug it in. I'm going to pick something convenient. I'm going to pick negative 2. Why is negative 2 convenient? Because 6 minus minus 2 is 8, and the cube root of 8 is 2. So it's easy to evaluate. So I plug in negative 2, I get the cube root of 8, which is 2, and 2 plus 3 is 5. And can I take the square root of 5? Yeah, I mean, it's not a nice number, but it's a real number, right? It's the square root of a positive number. On the other hand, if I pick something larger than 33, like 34. That's a terrible choice, James. 6 minus 34 is negative 28. I would love something that was more like a cubic. I guess I could pick 35. 6 minus 35 is, nope, that's even, fine, I have to go bigger. Fine. I guess I want to get all the way to 64. So 6 minus 70. So I pick 70, which shouldn't work because it's outside of the domain we found. 6 minus 70 is negative 64. The cube root of negative 64 is what? Sorry, I'm not very good at hearing. Negative 4. And negative 4 plus 3 is negative 1, and the square root of negative 1 is a problem. So it seems like we found the right domain here. Things that are in it seem to work. Things that are not in it seem to not work. So let's go ahead and try that. All right, let's just do that instead. So it looks like our domain is everything from negative infinity, which is usually an INF. The instructions usually tell you how you should enter infinity. They don't here, but that's usually the right choice. If it's not, we'll figure it out. Comma 33. Bracket. Let's see if it works. I guess I should have previewed. But there, we're good to go. Okay, cool. All right. As usual, you should ask questions if you have them. Let's go the other way, though. So let's do the other composition. Well, I should say the reverse direction, because there's many compositions. I guess technically all 4 of those are the ways you can. Why are you popping up? Go away. Did I click on that instead? Maybe that's why. So let's do the other composition. G of f of x. Same idea. It's going to be g of the inside function. And I'll point out here, we have to obey the inner domain. So right here, I already know that x is going to have to be bigger than or equal to negative 3. For sure. And then maybe also we'll lose something else. But definitely the biggest the domain could be is all the real numbers bigger than or equal to negative 3. And maybe it's going to be a smaller set than that, actually. Probably won't be, but it could be. So let's see, that's going to be, so g of some stuff is the cube root of 6 minus that stuff. And then the stuff is the square root of x plus 3. And no, there aren't any other domain issues here, because the cube root of whatever is fine. As long as the insides are real, positive or negative, we're really good to go. So here, our domain is going to be just x plus 3 has to be bigger than or equal to 0, or x has to be bigger than or equal to negative 3, or everything from negative 3 to infinity. This is also why I like to start these problems by finding just the domains of each of the individual functions, because it's going to help me in the long run. And then if I'm going to type this into Desmos, I'm going to write it as the insides are x plus 3 to the 1/2, 6 minus that, and then parentheses all of that to the 1/3 power. Cool. Something I want to point out here. Not you. Why do I keep clicking on the wrong thing? Terrible. Sorry. So if we go to enter that, if you really feel like the square root is just the way you have to write it, I think you can make that work. If you click on this, it's probably, I don't know, operations, exponents. It might be exponents, probably exponents. So you could do this if you really, really wanted to. But oh, look, see, you can't. It's still going to come out the way I said it should be. So if you want the bth root, it's raised to the 1/v power. You don't really have an option. Great. It's good not to have choices sometimes. So we know it's going to be the 1/3 power on the outside. And then I want some parentheses. And then inside those parentheses, I want a 6 minus x plus 3 to the 1/2. And I said 6 minus x plus 3. And we said the domain was everything bigger than or equal to negative 3. Bracket negative 3, comma. Do I need the slash? No, I don't. Okay. Positive infinity, which you just write as infinity. Let's check it out. Looking good. Okay, we'll do one more of these. I specifically want to look at F with F. I don't care about G with G. I'll point out that the domain for G with G or G composed of G is going to be everything because both of the functions themselves have domain of everything. So let's look at F composed with F. And I despise this notation. Despise is probably a little too strong, but I really, oh, sorry, you can't see it. Apologies. I really don't like this circle notation. It's not helpful. It's not explicit. It's not telling you what's happening. Whereas this much better notation, in my opinion, is better. You should read this as f of x. Again, I think I said this last time, but I'll say it again every time. Say the word of. It is an important word. It notates the functional relationship that we have. So really, really important to recognize that we have functions here and they depend on what the input is. So f of x was the square root of x plus 3. So we're going to have f of the square root of x plus 3. Again, we know right from the get-go that x is going to have to be bigger than or equal to -3. And then we're going to have the square root of our stuff plus 3. So this one might have an additional domain restriction. So let's figure it out. We know x has to be bigger than or equal to -3. And then we also know that these entire insides here, the square root of x plus 3 has to be bigger than or equal to 0. And here's a place where it's easy to make the wrong decision. When you take a square root, let me just ask, what's the square root of 16? Right, just 4, not -4 and +4. So this quantity here, the square root of x plus 3, no matter what value you plug in for x, this here is always going to be greater than or equal to 0. And then if you add 3 to it, it's still going to be greater than or equal to 0. So there's no additional domain restriction here, because no matter what we are picking for x, as long as it's in the domain of the inside function, this quantity is going to be non-negative. It's actually always going to be bigger than or equal to 3. So we're safe. I'm going to do another one like this, though, that's not here, because I think it's worth seeing how that can change. But just to answer the web work part of this, oh my gosh, James, come on, be smarter. The composition here was the square root of the square root of x plus 3. So I like to write these from the inside out. So I'm going to write the x plus 3 inside part first. So I have my x plus 3 to the 1/2. And then, so just as a reminder, right, it's, oh my gosh, I can be smart. So right, there's my inside x plus 3 to the 1/2, and I'm going to add 3 and then take the 1/2 power of all of that. Click on the thing you need, not the thing you don't need. So I have all that plus 3 and then all of that. So I need a left parenthesis and a right parenthesis raised to the 1/2 power. And then we said the domain was the same as this one. So let's just copy it, paste it, make life easy. We're good. Cool. I think you all can do that last one on your own. But let's talk about how you might deal with something just slightly different, like, sure, f of x equal to the square root of x minus 16. 16 is that cheap? Yeah, let's go a little bit smaller here. Sorry, I'm not trying to be too crazy here. It's not really a big deal, but I just don't want the numbers to be gross. Let's say x minus 4. The domain for this original function is clearly all x bigger than or equal to 4. You can set x minus 4 bigger than or equal to 0. You get x bigger than or equal to 4. What I really want to look at is, what about f of x? That's going to be f. I wrote the notation I said I really hated. Sometimes it just comes out. Sorry about that. F of x, which is f of the square root of x minus 4, which is then going to be the square root of my stuff minus 4, and my stuff is the square root of x minus 4. We know from right here that for sure x has to be bigger than or equal to 4. No matter what happens next. Ooh, yeah. Oh, there's one. We're gonna do one more with this, and then we'll be done. I promise. Well, with this part. So then I also have to say here that for my domain, that the inside stuff the square root of x minus 4 minus 4 also has to be bigger than or equal to 0. So then if I'm going to try and solve this, I'm going to get the square root of x minus 4 bigger than or equal to 4. I'm going to square both sides. I'm going to get x minus 4 bigger than or equal to 16. I'm going to isolate x, and I'm going to get x has to be bigger than or equal to 20. So my domain here actually is a lesser region. It's not everything from 4 to infinity. I'm cutting off all the stuff between 4 and 20, and then we can say everything from 20 to infinity. Because even though I could totally plug in like 5 right here, 5 minus 4 is 1, the square root of 1 is 1, 1 minus 4 is negative. So my domain here for this composition is everything from 20 to infinity. Where's all my paper? One more tiny thing to say about this. Let's say we still have the same function f of x. And g of x is equal to x squared plus 3. Clearly, the domain of g of x is all real numbers, right? It's a polynomial, but it doesn't have any of the things we look for. And if I look at g of f of x, this is where it's, if you're talking about domain, where it's really important to make sure you're looking at the composition. So g of f of x is g of the square root of x minus 4. And right there, before I say anything else, I'm going to remind myself, oh, inner function is the most important function, and the domain of that inner function has to be obeyed, no matter what else happens after the case. So then, if I plug this in, g of x is x squared plus 3, g of some stuff is my stuff squared plus 3. And then if we simplify this, a squared is just the stuff inside the square root. So I end up getting x minus 4 plus 3 equal to x minus 1. And the domain is still x bigger than or equal to 4, or if you prefer, everything from 4 to infinity. Even though if you just looked at this end result here, it would look like the domain could be all real numbers. But the problem here is that you can't plug in 3 to this original expression, because 3 minus 4 is negative 1, and the square root of negative 1 is not real, and it doesn't matter what happens after that. If you really want to see it, you can also look at Desmos. I know it's very exciting. So if we look at Desmos, you can do a square root in Desmos. Just type SQRT if you really like that notation. Square root of x minus 4. There it is. And then we're going to square it. Not all of it. So look, it starts at 4. Right? Stay there. Right? There's the first point you get. You don't get any of the smaller values of x, even though if you were to graph y equals x minus 1, they're the same. It's just y equals x minus 1 has all of the domain, and y equal to the square root of x minus 4 squared plus 3 doesn't have all of the domain. Kind of neat. Okay, questions about any of that domain stuff before we looked at the next web work in this particular homework, because it was asked about. Yeah. I'm not writing your test. I don't know. This is not, so generally on the test is not a good question for me because it really depends on your instructor. Some people might give you a graph, some people might not give you a graph. I would say generally people are probably not giving you a lot. They might sometimes, it depends on what they want you to do. Sometimes they might ask you to find the range graphically, but oftentimes they might just expect for you to know what the graph looks like. But really, the better answer is you should ask your instructor. Other questions? Yeah. How I got the which part? Sorry, I'm sorry. You're saying where? Paper like at the bottom. Mm-hmm. Like when you got the domain in like 20. Sure. Yeah. Say that last part one more time. How'd you get the 16? Oh, the 16. Yeah. So what I did here, and you're right, I didn't show my work, was I went from this inequality and then I squared both sides. So that the square root of x minus 4 squared is just x minus 4, and 4 squared is 16. Now I'll point out, doing this Oh yeah, I was gonna say that over here. So here I kind of avoided the issue of making the wrong choice here. But if you weren't paying attention, I'm like, well, I should probably solve that. You might end up domain is actually less than it should be. Because if I start trying to solve this, you can solve this. You can say the square root of x plus 3 is bigger than or equal to -3, which technically we know it already is. But if we weren't paying attention and then went and squared both sides, you would say, oh, well then x plus 3 has to be bigger than or equal to 9, which means x has to be bigger than or equal to 6, which isn't true. X doesn't have to be bigger than or equal to 6. It just, this gives you kind of a, what's called like an extraneous solution to an equation that we don't really need. So sometimes we just have to be thoughtful and be like, okay, well, I know this is already always positive or not negative. So this quantity is certainly already not negative as well. Be extra careful when you're looking at these domain things. Cool. Let's look at the other thing that I was asked about. Oh yeah, definitely here. So the other thing here, and the other web work question that someone asked about, I think is kind of a funky question because in my opinion, there's lots of correct answers to questions like this. This one maybe less so than usual, but yeah. So we're given this function and we're asked to write it as a composition of functions. And really, yeah, I'm gonna give two answers here. Really what I'll say is the only kind of wrong way to answer this is to say that the inside function is x. And even that's not wrong, it just feels like you're kind of not giving it as much of an effort as we could be. So our function u of x is equal to cosine of x over 7 plus cosine of x. Sure. And so I want to find an f of x and a g of x. I know. I just want to write it down here so I can still see it. So that f of g of x is equal to u of x. So that's what I'm looking for. I want to find an f and a g so that when I do the composition, I get that. So here would be a technically correct answer, but really, really not exciting. I could say that g of x was x and f of x is cosine of x, 7 plus cosine of x. Technically, that fits the bill, because if I do f of g of x, everywhere I see an x, I plug in g of x, which is equal to x. Feels kind of lackluster. Let's look at a totally bizarre answer. So here's the thing, and this is why I don't like this question, because you can make up lots of kind of really, I'm going to say stupid answers, because there are lots of wrong ways of answering this that are still technically right. But WebWork probably is looking for one very specific answer here. So here's a really, really bizarre way of writing it. I'm going to say that g of x is, yeah, let's be really silly about this. Let's say that g of x is e to the x. Where would that come from? From my brain. And f of x is cosine of the natural log of x over 7 plus cosine of the natural log of x. Sorry, there's too many parentheses there. Technically, this is correct. It is not the right answer in WebWork, I'm almost sure. I mean, I guess I could try putting it in, but I'm pretty sure it's not what they're going to want. But if I do f of g of x here, f of g of x is f of e to the x, and then I plug in the e to the x wherever I have an x there, and I get cosine of the natural log of e to the x over 7 plus cosine of natural log of e to the x. And guess what? The natural log of e to the x is just x. So this totally works. But again, really not the intention of the problem. The intention of the problem, in my opinion, was probably to let your inside function be cosine of x. So, and when you're trying to determine what the composition, like what two functions should make up the composition, you're usually trying to identify what the inner function is first. So I'm thinking, okay, my inner function is most likely something that's showing up maybe once or twice, is easily identifiable. So I would guess that g of x was cosine of x. And then I want f of g of x to equal cosine of x over 7 plus cosine of x. Oh, I want a parentheses there. Sorry. Parentheses. Ah, that's terrible. I've ruined it. Let me try again. Sorry. G of x is cosine of x. And I want f of that g of x to end up equaling cosine of x over 7 plus cosine of x. So then I'm going to replace the g of x's with just x, so that my f of just x is just x over 7 plus x. And that's probably the most correct way of answering this question, even though there's literally 1,000 different correct ways you could do it. You could do something else really silly and say like, g of x is 7 plus cosine of x. And then my f of g of x needs to be, well, I need to take my g of x and subtract 7 to make sure the top is just cosine, and then my bottom is just g of x. So here I could say that my f of x is just x minus 7 over 7. And that would also be a totally valid answer. I wonder if they'll take that. That seems like they might take it. Let's find out. Just for the sake of knowing. So if I say that f of x is x minus 7 over x. I wrote 7 on the bottom. Sorry, that should be x minus 7 over x. Let's find out. Let's see how flexible WebWork can be here. And then my inner function, I said it should be 7 plus cosine of x. Do you make sure you're using the right variable? Right, if your function is a function of t, I should be writing my functions here as functions of t, not x. Let's do it. Oh, that's neat. Surprised. Now I want to try different answers, but that's not the point of this. So I'll do that on my own time later. But I really want to try the natural log one. And I'm curious if that one will work out. It probably wouldn't work out because I will say there is something about what I've written here. Yeah, that's actually a good point, James. So I will mention that one thing that's kind of wrong about this answer down here is that this function here, actually, this is a good question. What's the domain of this function? Do we have any square roots? Do we have any logarithms? Do we have any potential division by 0? You can say yes to potential. There is potential division by 0. But do we actually ever get division by 0? Well, it's really, really good to know that cosine of x is always between what two numbers? Right, 1 and -1. And if it helps you to see it, the graph is really, really nice to, you should definitely know the graph of cosine and the graph of sine. Here's the graph of sine. Here's the graph of cosine. Turn it on. So definitely all the output values are between -1 and 1, or the range is between -1 and 1. And so with that in mind, it certainly is impossible for this denominator to be anything other than between 6 and 8. So it will never equal 0. So this function has a domain that is all real numbers. Whereas the way I've expressed it down here, technically I've got some problems because I don't know, it's dicey. But cosine natural log of x, right, the domain is everything from 0 to infinity, exclusive of 0. So messing with the domain might make my answer not correct. Anyways, we should ignore that answer because it's silly and not purposeful. Cool. What time is it? 2:42. What time? We were here until 3:30. All right. So domain, range, composition of functions. I think we've said a lot of the things we need to have said about it. Did you all start talking about semi-log and log-log graphing? Okay. Anyway, no, none of the 3 classes. Okay. That's all right. Yeah.
There was like in 1.4,
Mm-hmm.
was like find the equation of the graph that results from reflecting y.
Oh, sure. We can talk about some of those. Those are good. I like those questions. So yes, I remember seeing a few of those. Let's look at one something like, so let's say we're given, yeah, we'll start off with an easiest example. So let's say we have like this good old f of x equal e to the x, kind of a classic function here. And just so everybody knows, right, e is a real number. It's irrational. It has a never-ending decimal. It's approximately 2.7, but it is just a number, just like 5 or the square root of 2, just a irrational number, sorry. And the graph of this, oh, that's what I was gonna say earlier. The graph of e to the x looks like this. And you have an intercept at 0, 1. You have a horizontal asymptote at y equals 0. The domain is everything. The range is all positive numbers. It's also worth noting that this is an increasing function, which just means that visually it gets bigger from left to right. There is kind of a more formal definition of increasing, which just says that if an x value is smaller than another x value, then the corresponding y value should be smaller than the corresponding y value. So for increasing, we say that if a is less than b, then f of a is less than f of b. Right, so you could imagine like a being here and b being here, and a is less than b, and then f of a is less than f of b. That's the more formal way of talking about a function being increasing. I'll talk about decreasing in a minute. And then just because we're already here, let's talk about the inverse function as well. G of x equal to log base e of x, which is more usually written as g of x equal to the natural log of x. I will strongly emphasize here that it's really, really good to know that this is just an abbreviation. Right, just like ST period is an abbreviation for the word street. They have the same meaning, they're just written slightly differently. But if you see natural log of x, or some people like to say ln of x, that just means log base e of x. Just like if you see log of x, that just means log base 10 of x. We've decided to abbreviate it because it comes up so often, and we're trying to save money on ink. All those 10s we didn't write in our textbook, all those e's we didn't write. Probably, maybe. Actually, I think I think there might be some actual veracity to that, but whatever. So graphically, this function is the literal inverse of that function. So all of the x and y things interchange roles, and we have a graph that looks like this. We have an x-intercept of 1, 0, right? The x and the y is interchanged. 0, 1 interchanged to become 1, 0. Instead of a horizontal asymptote of y equals 0, y interchanges with x to give us a vertical asymptote of x equal to 0. And just like for inverse functions, the domain, the x things, and the range, the y things, are going to interchange. So here, the domain is all positive numbers, which we already knew was true for regular logarithms. And the range is all real numbers, everything from negative infinity to infinity. I do want to point out that even though this graph looks like it's slowing down how it's increasing, and it is kind of, it never like flattens out. It keeps getting bigger and bigger and bigger forever and ever and ever. It just looks like it's gonna take forever because it does it so really, really slowly. But it does keep increasing. So both of these functions are increasing functions, and I don't remember if I said this in this class or a different class, but stop me if I said this before. Did I talk about the right hand thing? No, look at your right hand. My right hand is not great because I'm old, but it's fine. Not great for this. It's fine for everything. So if you look at this line right here on your right hand, it looks a lot like the e to the x function. If you look at this curve down here, and this one's really hard to see on my hand, but like the one kind of across the meaty part of your thumb there should be a natural log of x function right there. Kind of great. Make sure you do look at your right hand though. I know most of us are right-handed, so you might be writing and look at your left hand. Less good. That function is e to the negative x and the natural log of negative x, which is not as useful. So okay, still useful. All right. So we were talking about doing some transformations of this, specifically reflecting it across some lines. So how are we going to reflect e to the x across the line, say like y equal to 4? Let me make sure. My papers are way out of order here. Oh my God. Sure. Oh no, they're not. I'm just imagining things. Try to keep things in order for later when I post the notes. Sorry. Cool. Yeah, you're good. Okay. Okay. So I want to reflect y equal to e to the x across the line. We'll start with y equals 4. Okay, there's 0, 1. This is not going to be to scale, such as life. Here's my line, y equals 4. I probably made that too high for my comfort, but okay. So when you're reflecting across a line, you typically want to kind of pick a point you have. And the other point that I really have that's nice here is 0, 1. So if I reflect that point 0, 1 across this line, well, the distance from 0, 1 to that line is 3, right? From 1 to 4. So I need to go another 3 above that to find where that point's going to reflect to. So if I go 3 above it, and that's why I'm kind of, yeah, I probably have enough room here. Try to make it look nice, about right there. So 1 plus 3 plus 3 is 7. So that point there is going to be 0, 7. And then the horizontal asymptote that was at y equals 0 was 4 below the line of reflection. Now it's going to be 4 above the line of reflection at y equals 8. So my new graph, which I'll draw in green. You guys can kind of see the colors, right? Like they're not like totally useless. Try and use different colors. Okay, great. So I'm just reflecting all of this. Trying to make it look right. There's my reflection across the line y equals 4. I took that graph and I flipped it up like that. So how do we find the equation? So the way to find the equation of this graph is to imagine it as two transformations done one after the other. So if I actually had to like do this in 2 steps, I would probably do it this way. I would start with my graph, y equals e to the x, and I would probably reflect it across the x-axis first. So if I reflect it across the x-axis, I'm going to get this graph here. Algebraically, when you reflect a function across the x-axis, you are essentially negating every y value. So instead of having y equal to positive e to the x, this graph is the graph of y equal to negative e to the x. Or if you prefer, negative 1 times e to the x. And then I want to shift it up 8. So then I'm going to add 8. So that all the y values are 8 bigger than they were. So then we're going to not draw it again. We're going to shift it up 8 and get y equal to negative e to the x plus 8. Or you might write it as y equal to 8 minus e to the x. Oftentimes when you have a couple terms and one of them is negative and one of them is positive, it's usually standard to write the positive one first, although not always. So it doesn't really matter. Okay. What about reflecting it across a vertical line instead of a horizontal line? Let's look at that. I'll try not to say this too often, but as usual, if you have questions along the way, you should ask them. I'm happy to say more about the things. I'm just going to keep talking until time is up, essentially, really, is the truth. So same function, yeah, same function. Now we want to take f of x equal to e to the x and reflect it across. Do we want it to be, what do I want? Let's say x equal to negative 3. Colors appropriately here, James. I will point out when you draw an exponential function like e to the x or 2 to the x or 3 to the x or 5 to the x or 7 to the x or any positive base to the x power, it should have this general shape. And importantly, it should not have a vertical asymptote, right? It doesn't continue going up like straight up. It should end with an arrow that's still kind of pointing up and to the right. And then we're going to I suppose instead of just trying to graph it, I should just like do the things to try and graph it. How do I do this? It's always harder when you're reflecting across a line that's an x equals something. So let's see here. 1, 2, 3. Yeah, I do find this more challenging. I'm not going to lie. So if I was trying to make this happen, I would probably, what would I do? I guess I would do the reflection first and then the shift second. I don't love it, but I'm going to try and make it work. So reflection across the x-axis, across the y-axis. That's going to just take that and turn it around. It'll look vaguely like this. So when you reflect across the x-axis, you end up putting a negative in front of the entire function because all your y values become the negative values what they need to be. On the other hand, when you reflect horizontally across the y-axis, all of the x values have to be the negative of what they were to still produce the same corresponding y value. So we're going to get, this is the graph of y equal to e to the negative x. And here's where things get dicey. I want to shift this. How much do I want to shift this? Well, actually, let me ask a better question. Which direction do I want to shift this? To the, I mean, I know I didn't draw it, but if I was going to reflect this, right, this point is going to reflect 3 that way and then 3 more that way to be over there. And it's going to do like, I hate graphing this. Carefully. And then, like that, kind of. So I'm shifting it 3 plus another 3 to the left. Usually it's kind of like twice as much as you are far away from the axis of reflection. So here my axis of reflection was 3 away from the y-axis and I'm shifting it 6. In the previous one, my axis of reflection was 4 away from the x-axis and I shifted it 8. Not a coincidence, it's pretty typical. So I want to shift it. And again, I'm worried about this happening the right way because these ones are always tricky. I want to shift this left by 6. So here's what I know what I want to happen. I know that here, if I plug in 0, I get 1 as the result. And I want that point to move 6 to the left. So I want this point here to be 6 to the left of 0, 1. So I want this point to be -6, 1. So what I want to happen, sorry, it's all tilted, is that when I plug in -6, I want to get +1 as my output. So that means I need to have -6 plus 6 to give me a power of 0. So I think I want this to be y equal to e to the negative parentheses x plus 6. So then when I plug in -6, I get e to the 0, which is 1. That seems right to me. And so then if you wanted to distribute this, you could write it as y equal to e to the negative x minus 6. But I will fully admit, and many people always find it challenging when you have both a horizontal shift and a horizontal reflection. It always feels like you're kind of doing things backwards, but sometimes people read this as first doing a shift of 6 to the right and then flipping the whole thing across the y-axis and still coming out with the right thing, right? If you moved this graph 6 to the right, you'd have the point 6, 1, and then reflect that all the way across the y-axis, and you're going to get the point -6, 1. That would also work. It's just never the way my brain wants to make it work. I can't go off screen. Okay. So yeah, that's my final function here. And I guess there's my poor looking reflection. Don't judge me. Or judge away. It's fine. You can judge my drawings. I try to make them good, but they're not always good. There's something else I meant to say here. Oh, yeah. I will point out, I will draw it again because there's something I want to say. Can I draw it again? Sure. So really don't like drawing this, but it's fine. So here's -6, +1. So this function looks kind of like this. Should have a horizontal asymptote at y equals 0. So we're going to try to do our best to not actually cross the x-axis, even though it's hard not to sometimes. So this is y equal to e to the negative x minus 6. Yeah, it's a minus 6, right, James? Yes, it is, because x is negative 6, you get positive 1, yes. What I want to say about this, though, is this function, y equals e to the negative x minus 6, is decreasing, which you can totally see just looking at it, right? As you move from always from left to right when we're talking about increasing or decreasing, or really kind of anything about a function is usually from left to right, unless someone specifically says otherwise. And the way you would say this in a more definitive way is that if A is less than B, A is the left point, B is the right point, and I would just literally draw them in there. If A is less than B, then we should have that f of A is what compared to f of B? Bigger than f of B or less than f of B? Less than. Less than? Which one should the alligator eat? The f of A or the f of B? So let's take a look. Here's f of A. There's f of B. I know it's kind of hard to see because it's kind of small, but which of those is bigger? The f of A is bigger. So the f of A is the bigger one. So to be decreasing, the left thing has to have the bigger y value and the right thing has to have the smaller y value, which is opposite of increasing, right? Where the left thing has the bigger, the left thing has the smaller, and the right thing has the bigger y value. Cool. All right, 3 o'clock. See you guys again on Tuesday. What are you going to do between now and Tuesday? Lots of things. When's your first test? Oh, question. Okay, statement, comment, whatever. That sounds right. Yep. So is it not open yet? Oh yeah, I usually wait to have them open until like after. Yeah, so no. There's a purpose, a reason, a method to the madness. The point is that I want you to have gone to all of your Monday through Friday classes before you do the reflection. That's kind of it there. But I will also mention the reflection takes like 5 minutes. So just I know it's like it'd be nice to just have it off your plate, but just do it on Friday or Saturday. It won't be that bad, I promise. And then you'd be like, hey James, can you talk about this next week? And I'll be like, yes. So that's the whole idea is you've seen what's happened Monday through Friday, and then you can tell me we did these things, we want to see these things. Yeah. Okay, that seems reasonable. You want to know when the first one for Dedell is? October 14th. Yeah, right. See. What else? So Alameda is the 28th. What about Lewis?
13.
The 13th? That's a Sunday.
Oh,
Or is it November 13th?
yeah.
Oh, wow. Okay. Wow, that's even much later. For Lewis? Okay, cool. And then Alameda, Lewis, and Varn.
Also 28.
Okay. So that's great. Ah, it's so perfect. Like things are working out very nicely having Dedell in one section and everybody else in the other section. Because his tests are on a totally different timeline, and he's not using web work, and you're all using web work, and you're all having your same first test on well, not the same person. You're all having your first test on the same day, which is October 28th. Which is why Monday? Monday. I do not love a Monday exam personally. I think a Wednesday exam is the best if you have a Monday, Wednesday, Friday class. Because like Friday, you're like, really, you made us do it on Friday, and when Monday, you're like, but it was the weekend. So, well, you all will have plenty of notice that the exam is going to be on a Monday, and you'll have to make sure on that Sunday that you take it easy, make sure you get a good night's sleep, all that stuff. Yeah, I'll be here. Okay. Yeah. So that means, so the Thursday before, which will be the 25th. 24th, thank you. Yeah, we should definitely have an exam review, but that's not now, that's then. Okay, we've talked about functions a lot. We've talked about shifting functions a lot. I feel like there was, no, so, okay. Try not to get too ahead because the other class is I do want to, let me do one thing real quick here. I just want to look and see what's on. I feel like Tim's usually the easiest to figure out what's going on with. Where'd you go? Sorry, I was trying to. Oh, he's got all sorts of stuff on here. So where are we at? Discussion worksheet 2. Can we see this yet? Can you all see this yet? Okay, cool. Didn't mean to download it. Oh yeah. Okay, cool. Yes, awesome. Okay, great. We should definitely talk about the thing I wanted to talk about. Oh, Watt's probably strong. Oh yeah, there were some over problems too. So yeah, let's talk about semi-log and log stuff because it is going to come up. It should come up for all of you. Everyone should cover this. So this is broadly titled semi-log and log-log relationships. So really the idea here is to make data more easy to comprehend. But sometimes some data values are really large and others are not, and it's kind of hard to graphically make them useful. For example, if we had data that we knew fit a relationship of something like, I don't know, y equal to 3 times 5 to the x. Sorry, let me make sure my example is what I want it to be. I don't know if it's 3 times 5 or 5 times 3. Oh, it's over here. There we go. Yep, 3 times 5 to the x. The issue with something like this is that the y values get large really fast, right? You start plugging in values for x and y. If x is something like 0, 1, 2, 3, or 4, well, 0 is not so bad. 5 to the 0 is 1. 3 times 1 is 3. 5 to the 1 is 1. 3 times 5 is 15. 5 squared is 2. 5 squared is 25. 25 times 3 is 75. 5 cubed is 125 times 3 is 375. 5 to the 4th is, okay, we're getting kind of big. 625 times 3 is 1,875. So the y scale here is much, much larger than the x scale here. And if you try to graph this in any sort of meaningful way, it's going to just get gigantic. So, okay, zoomed in, this seems reasonable. But if you start zooming out, it just starts to look like you got this horizontal bit and you got this pretty much vertical bit. They're not actually horizontal and vertical, but that's not what the graph is telling us if we don't look at it closely. So what can we do? Well, we can do this thing where we take the logarithm of both of sides of this equation. So we're going to rewrite this, or rewrite maybe not the right word here. We're just going to take the log of both sides, the log base 10. So we're going to take the log base 10 of both sides to essentially dampen the value of y, right? If you take the log base 10 and 1,875, it's like between 3 and 4. So let's do that. So we take the log base 10 of y equal to the log base 10 of 3 times 5 to the x. We're going to do some simplifying here. So we're going to rewrite this as log of y equal to, I'm going to use some log rules here and say that log of this times that is log of 3 plus log of 5 to the x. I'm going to take a minute to come back to this. And then we're going to simplify one more step and say log of 5 to the x. We can bring that x down in front and say we have log of 3 plus x times log of 5. And the idea here is that we're going to think of we're going to think of log of y as a new variable, capital Y. And yes, you do use a capital here to try to distinguish between your lowercase and your capitals when you do something like this. And capital Y is going to equal Write this again, sure. Capital Y is going to equal sum m times x plus b. In this case, it's going to be log of 5 is our m times x. I know I wrote that in the opposite order, totally fine. Plus log of 3. There's your slope of your linear function. There's your y-intercept of your linear function. So this exponential function, exponential relationship, if you change the y variable into log of y, the y values get dampened and you get a linear relationship. So graphically, what we've done is we've turned this wild looking exponential equation, wild, maybe an exaggeration there, but this exponential equation into now something that looks like this. Log of y, which I'm just going to write as y still, is going, let's use capital Y just to be expressive here. Y is equal to log of 5 times x plus log of 3. That, whoa, I got too many x's. How did that happen? Sorry about that. There we go. Okay, straight line, like I said, right? Okay. And so here you can see, right, the y-intercept is your log of 3 value, which is approximately 0.47712. And your slope is log of 5. So you pick another point like this, yep, that one there, I had it right on there, right? The slope would be the difference between the y values over the difference in the x values, which, okay, we could calculate. 1.87 minus 0.477 is about 1.4 divided by 2 is about 0.7. And if you find log of 5, oh yeah, it's about 0.7. So the slope is about 0.7. By the way, I never knew you could do that. Like someone just showed me that, like you can just type things in Desmos and it'll be a calculator for you. It's kind of great. I had no idea. So this is useful because it helps us see that, okay, if we have some sort of exponential relationship and we take the logarithm of all the y values and then graph that, it will be a linear relationship. And so what we're really going to do is we're going to take a bunch of things, a bunch of data points, plot them, and then try to see if the relationship is linear or exponential or power, which we'll talk about in a second, by seeing if it's either a linear function when we do the semi-log graphing, where you do the log of y and just regular x, or when you do the log-log graphing, where you're using both log of y and log of x. And yeah, we have enough time. So let's look at that. So let's look at the other kind of example here, which is instead of having an exponential function, and I should actually go back and say one more small thing here. I should just tell you that if you have y equal to some exponential function, like a times b to the x, exponential because you guys can tell me if you can't see it. It's exponential because you have b raised to the x power. If that's the case, then the semi-log graph will be linear. Or the converse of that, if the semi-log graph is linear, then we know the original relationship was exponential. In a similar way, we will see that for power functions, like y equal to 5 times x to the 4th, where you have x to a power, the power function will have a linear graph on a log-log scale. And the way you kind of get there is by taking, again, you take the log of both sides. Say log of y equals log of the other side. You break apart the other side using your logarithm rules. The log of y equals log of 5 plus log of x to the 4th. Use the power rule to bring down the exponent there. So log of y equals log of 5 plus 4 times log of x. But now both log of y and log of x are showing up, and those get replaced by stand-ins, capital Y and capital X. So we're going to say that capital Y is equal to 4 times capital X plus log of 5. So in this is linear on a log-log graph with a slope of 4 and a y-intercept of log of 5. Not very exciting so far, I fully admit. But here's where it gets interesting. We're going to take some data points. And actually, let me just do it the easy way. Easy-ish way. Where'd you go, Tim? That assignment looks super fun, by the way. I mean, okay. It looks like it's going to be some work, but it is an interesting assignment. Interesting is a better word. That assignment looks very interesting. If we look here, you can see that in Tim Lewis's web work, assignment number 2, I was looking through the questions earlier. I just want the problems, James. Okay, I don't remember where it was, so let's have to scroll through them real quick. Not you, not you, not you. There we go. So let's read this. The following table is based on a functional relationship between x and y that is either an exponential or a power function. You use an appropriate logarithmic transformation and a graph to decide whether the table comes from a power function or an exponential function and find the functional relationship. Solve the relationship for y in terms of x. Okay. How do you do this? Well, there's 2 ways to do it, which I actually cover in the video I posted in Canvas about log-log, semi-log using either Desmos or Google Sheets. But I think, especially for those of you in Lewis's class who are looking at that other assignment, the Google Sheet way is kind of the more informative way of doing it. And yeah, we have enough time. Let's do it. So I'm going to take this data. Hopefully it copy pastes nicely. We'll find out in a second here. I don't need that 0, so I'll live. Can I just open Google Sheets, please? Give me a new sheet. Why are you taking forever? Okay. So give yourself some room. Let's paste it right here. Yeah, it worked. Awesome. So here's what you want to do if you're doing it the Google Sheets way. You first want to label your columns. So this one was X. I don't need a caps lock. This one is Y. We're going to try and test all the relationships. So first we're going to test this one, which will just test to see if it's a linear relationship. And then we'll test X versus log of Y. And also log of X versus log of Y. Fun fact, if you do it this way, I don't know why, but you need a space column between your 2 columns because just, I've done it not with the space and everything is messed up. I don't know why, it just is. So you want your X versus your Y's in columns next to each other, and then your X versus your new Y's in columns next to each other, and then this way. So I find doing it this way is the easiest way to do it. And then this is pretty easy. I'm just gonna say that X is equal to B2. And then instead of typing the rest of them, I'm just going to grab that little dot there and drag it down. Boom. And instead of trying to actually use a calculator, I'm just going to say this is equal to log of C2. Great. And then it just wants to fill it in for me. Oh, how lovely. And then for log of X, it's going to equal log of B2. Oh, B2. Cool. And then drag that down to get the rest of the values. That's log of 2.8, log of 3.3, etc. And then finally, log of y is going to be the same here, but I'm still just going to write it out because it's easier. That's going to be log of C2. And then fill it in. There we go. So there's all our values. And now we're going to plot them on a graph. Specifically, these x's versus these y's, and then these versus these y's, and then these versus these. So let's do this one first. So let's grab both of the columns, including the names, X and Y. And then I have to remember how to do it. I think we insert a chart. Yeah, chart. Cool, there's our chart. And then we want to see how good of a fit this is, which is clearly not, right? It's not linear. We already knew it wasn't linear. But here's how you tell how good or not good it is. You remember how to do it. You go to customize. You go to series. Yeah, and then you go down, 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 and you click on the trend line. There's the best fit linear line. I know linear line is a repeat there, but okay. And then you also click on showing R squared so that you can see how good a fit it is. The closer that number is to 1, the better your fit is. The closer it is to 0, the more terrible your fit is. So now we're going to do the same thing. Oh, and there's one more thing you can do, which I always forget where it is. I think it's on chart and axis titles. If you, why is it always hiding from me? Sorry, it's always hard to find this last piece. I don't really need it right now, but I want it. Oh, here it is. It's always in the place it's already at. I just try to forget. So for the trend, is it there? Oh no, the label. It's the label. You can change the label to the equation so that it actually gives you the equation of that line. So there's your y equals mx plus b. If that was the best fit line, that's what I would say the equation was. But it's not, or at least we don't know it is yet because we haven't tested the other two. So we're going to do the same exact thing 2 more times. We're going to do it for these values. We're going to do the same thing. We're going to insert a chart. And then we're going to do the same things. We're going to customize. We're going to go series. We're going to go down to the trend line. And then we're going to include the R squared, and the label should be equation. And that's a pretty good fit. My R squared is 0.975. Let's see if that's the best, though. Also, so I'll point out, if this is the right one, then we know that our relationship is going to be exponential because this is a semi-log relationship that is linear because it's log of y versus regular x. Let's try the last one here. Let's just cover this other one up because we know that's not the winner. So then we've got these guys. Same deal. Insert, chart, and then go to the same place. You're going to customize. Let's move you out of the way here. Cool. So we customize. We go to series. I always forget. Go to trend line, and then the R squared, and then we want the label. And this one is clearly the best one. R squared is 1. Okay, we're not done yet, though. So I'm going to write things down here. For this data, I just want to write down what my equation is. So also, point of interest. For this one, my R squared is 1, and my equation is written slightly wrong there. For whatever reason, when you do this, the independent variable always just shows up as x, not as whatever you call the independent variable column. So even though my independent variable is actually log of x, they are writing as just x. So I know that my equation should actually be, I'm going to write it down and then I'll show it to you. Log of y equal to negative 2.3 times log of x, not x, plus 1.05. That's what my equation is like. And then if we look back at the question, our job is to use an appropriate logarithmic transformation, use an appropriate logarithmic transformation and a graph to decide whether the table comes from a power function or an exponential function and find the functional relationship between x and y. Solve the relationship for y in terms of x. Simplify as much as you can. There should be no logarithms in your answer. Okay, so we've got this equation here, which you could have, I guess, if you wanted to, although I don't think you need to, start off by writing capital Y equals negative 2.3 times capital X plus 1.05. But there's no need to do that, just so people like to do that. So now I'm going to try and solve for Y. Then to get rid of this log of Y, and how do I undo a log of Y? Oh my God, the words don't want to come out of my mouth. How do I undo log of Y? I write both sides as powers of whatever the base is. In this case, the base is 10. So we're going to write 10 to the log of y equal to 10 to the all that. And then we need to simplify because, well, our answer can't have any logs in it. 10 to the log of y is just y. That's why we did this in the first place. Over here, 10 to the something plus something, we can write as 10 to the first something, negative 2.3 times log of x, times 10 to the 1.05. Out of the law of exponents, right? 10 to the a times 10 to the b is equal to 10 to the a plus b, and vice versa. 10 to the a plus b is 10 to the a times 10 to the b. Here, we're going to simplify further because we have to and because we should. I'm going to rewrite this as 10 to the, instead of writing it as negative 2.3 times log of x, I'm going to make that negative 2.3 the exponent of x in the logarithm. So it's 10 to the log of x to the negative 2.3. Still times 10 to the 1.05, which I would love to write for as a decimal approximation, but I probably should just name it as 10 to the 1.05. Finally, just like 10 to the log of y was y, 10 to the log of some stuff is just going to be that stuff. So we're going to get y equal to x to the negative 2.3 times 10 to the 1.05. Now, here's what I think is kind of cool about this. If you actually took that data, and it's easier to do in Desmos, but if you took that data, and hopefully it works here, and you plotted it, can I just do that? Yeah, awesome. Is that the same data? Double check. Not that, not that, not that. There we go. Yeah, same data. Cool. So there's my points. And then you could actually just draw the line, or the, not the line, the equation we just came up with. The y equals, I'm going to write it as 10 to the 1.05 times, not x. I guess I can just write x, but I can write times x to the negative 2.3. Nope. Whoa, 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 whoa. Sorry. Look at that. It exactly goes to the points. And it should be exact because our r squared was equal to 1. Let's write our answer web work just to make sure it's right. So I had 10 to the 1.05. I don't love that. I guess I need some parentheses around that. Maybe, I don't know, maybe not. Don't chance it. Times x to the negative 2.3. Find out, was I right? Yeah, great. That's awesome. Cool. So now I'll say one more thing. Yeah, I got 3 minutes. One more thing. So this is the better. This is the more informative way to do this kind of problem, where you're actually kind of testing both things and seeing what works. But we totally could have done this in Desmos, probably doing what feels like less work. So if you want to try doing this in Desmos instead, what you could have done is taken this data and said, well, do I think it's going to be linear or exponential, meaning linear for semi-log, or power function, meaning linear for log-log? Here's how you test that. If I think it's exponential, I'm going to try doing y approximately equal to some, well, I need y sub 1. Sorry, I got to use the correct subscripts there. Approximately equal to m times x sub 1 plus b. Not that good. And hopefully, oh my gosh, come on. Yeah, look at that. The r squared value here is 0.77. The r squared value there is 0.77. That's not a coincidence. It's doing the same thing. And then we're going to test to see if it's exponential by doing y sub 1 approximately equal to an exponential function. So a times b to the x sub 1. And the r squared values I don't think match up, because for some reason, I will be perfectly honest, I don't know exactly the reason for this. But if you hit the log mode here, then the r squared values I think do match up. Yeah, 0.9747, sorry, it's somewhere. 0.975. Yeah, that's right. Okay. So then finally, if we try the last one, so that was testing to see if it was an exponential because it's a times b to the x. We test the last one, y sub 1 tilde power function. So a times x to the b. Perfection. R squared equals 1. So we know that the relationship should be exponential. And then it even gives you the A and the B. Does it give you the A and the B? Yeah, look. Right? So I know I wrote it as 10 to the 1.05 times x to the negative 2.3. But look, there's my x to the negative. That's pretty close to 2.3. And if you check 10 to the 1.05, well, let's just check. 11.22, pretty close. Not exactly because things don't work. But yeah, so doing it this way will kind of just give you the equation. Although I will point out, if you entered this into your web work, it probably wouldn't come out right. You probably actually need to do the other work. So this gives you a good idea of what should be the right answer. I still think the Google Sheet way of doing it's probably the more you're learning something kind of thing. But both are useful tools. All right. I'm gonna stop talking because it's 3:30. Well, lovely rest of your day, weekend, and I'll see you on Tuesday or in office hours, which I have right now. Downstairs.